Doing problem 9 from practice exam 2. This is a pretty difficult problem for a couple of reasons. First of all, you're really going to have to use the graph a lot when you, the calculator, just to see exactly what's happening, where your starting and ending values of your integral are going to have to be. The first thing we want to do is just realize that when we do graph this thing, I'm going to try to just draw a little small version of the graph here. What does it look like? It kind of starts over here. It makes a little inner loop, and then it continues around, and then it makes a nice outer loop like that. So it looks something like that, and the goal here is to find the area that's enclosed by that inner loop right there. So what we first have to notice is that if you set your graphing calculator to graph normally, as in starting at theta equals 0, it does start right there, and then it graphs that little bit right there, which means that part of the graph is not going to concern us as far as the integral is concerned. We need to figure out where does that little loop start, okay? So what you can do to sort of help you to do that is notice that that starts when r is equal to 0, okay? So if I set my function equal to 0 and I solve, this is what I get. Theta is equal to the inverse sine of 1/3. Of course, that's not going to be the only place that happens, but it's a good starting point. So if you, from here, graph on your calculator, set theta min to be 0 and theta max to be that inverse sine of 1/3, what you can do is, what you'll notice is that what we're actually looking at is that piece right there. So if you start here, that's theta equals 0, and the end here, that's theta equals inverse sine 1/3. So the piece that we are really interested in starts at that. So this is sort of just to help you to see that we're just going to look at that top part right there. That's not what we're concerned with. So we don't really need those settings. So instead, what we're going to do is set theta min to be equal to that inverse sine of 1/3, and that will start on this little loop. And then what we'll notice is that the other place that it reaches 0 is if we go all the way around and come back, it's going to be 0 again. Well, where does that happen? It turns out for that one, remember that when we're talking about the unit circle, if you want to find another angle that has the same sign, which is what we're doing here, you say pi minus the one that you got, okay? So that would be the other one. However, we can also take advantage, so basically that means that if I start here, that's going to be the inverse sine of pi of 1/3. That's starting here, theta min. If I go all the way to theta max equals pi minus that's gonna enclose that little loop right there, okay? So that could be my lower and upper bounds. However, I could take advantage of symmetry and realize that if I only go down to here, right there, then I can just double the answer, okay? So what is that value? It's straight down, okay? So it can only be one of two things. It can either be pi, pi over 2, or 3 pi over 2. Remember that you can have negative radii as well on these things. So, and I've tried this, you can make theta max be 3 pi over 2, pi over 2, and let me make sure what I've got here. Yeah, pi over 2, not 3 pi over 2. 3 pi over 2, go too far. So just pi over 2. And that's going to tell us that we're in fact going to have a negative radius there. Because pi over 2 is straight up, but in fact the graph is below. So theta max can be pi over 2. Okay, so that's part of the reason this problem is pretty difficult, is because you have to figure out what these bounds are. So please play around with this. Set your theta min to be 0 and that, and you'll zoom in on this part of the graph. You'll see that it starts here and goes to there. Then set theta min to be that same value. Set theta max to be pi over 2, and what you'll find is that it starts here, it encloses half the loop, which is pretty much exactly what we want. So then we can use our formula and just double it to figure out the total area enclosed. Okay, so the formula that we have to use now is this one, the one that you can see on your formula sheet. Total enclosed area of a polar defined equation is the integral from a to b of 1/2 r squared, what r is the function of theta. So okay, so this again, remember that comes from the area of a sector. Okay, so we'll put this in, and now just remember that we're doubling it because we're only doing half of the area there. So if I double it, that's going to take care of that 1/2. So in our case, our integral will then be, and the bounds are what we were struggling with here. Lower bound, as we said, theta min, we have to put this for our lower bound, the inverse sine of 1/3, and then max pi over 2. Okay, so that's our bounds, our function, that one there, so 1 minus 3 sine theta quantity squared d theta. So that's the integral that we want to find. So again, mostly what makes this problem kind of difficult is the fact that these bounds are a bit tricky to find. You got to use the graphing calculator. There's really not too many other ways to do this without that calculator. Okay, so anyway, to do this antiderivative, we're going to have to expand it. So let's write this again. Pi over 2. Expand that, we're going to get 1 minus 6 sine theta, and then plus 9 sine squared theta. So now we've got to find the antiderivative for this thing. That's going to be theta minus, actually plus 6 cosine theta, 6 cosine theta. And then for that one, for the 9 sine squared theta, just let's recall that sine squared theta is equal to 1/2 minus 1/2 cosine 2 theta. Okay, so if I want to find that antiderivative, I'm going to get, let's see, what is that going to be? Plus 9 times 1/2 theta. And let's see, antiderivative there is going to be 1/4, so I'll have minus 1/4 sine 2 theta. Okay, and then we want to plug in our two bounds, inverse sine of 1/3 and pi over 2. Okay, so let's go ahead and combine some of our like terms here. We've got two constant terms, so 9/2 plus 1, that's going to be, let's see, what is that going to be? 11 over 2, right? So 11 over 2 theta. We've got a 6 cosine theta, and this 9/4 sine 2 theta. And we're evaluating this from the same bounds, inverse sine of 1/3 and pi over 2. Okay, so next thing, just plug these things in. So we're going to get 11/2 theta, which was pi over 2, plus 6 cosine, fix that, cosine of pi over 2 plus 9/4 sine. Let's see, if I double pi over 2, I'm going to get 2 pi over 2, that's pi. So that's what happens when I plug in pi over 2. Now I have to subtract off what happens when I get arc sine 1/3. So I'm going to have 11/2 inverse sine 1/3. And 6, subtracting off all of these so they all become negative, the cosine of the inverse sine of 1/3, and 9/4. Now on this one, I'm actually going to have to use a double angle identity on that. Sine 2 theta is equal to 2 sine theta cosine theta, so 2 sine of the inverse sine of 1/3 cosine of the inverse sine of 1/3. Okay. One more for that. Okay. So now we've got to try to simplify all this. We're going to have 11 pi over 4 Cosine of pi over 2, that's going to be 0. Sine of pi, that's also 0. So we're going to have minus 11 over 2 inverse sine 1/3. Make sure we're approaching our correct answer on this thing. Yeah, I think we're getting there. And then, let's see, what else do we have? Okay, so these ones here, we might have to consider a triangle on this. The cosine of the inverse sine of 1/3. So if you let theta be the inverse sine of 1/3, I don't want to run out of room here, let's try to squeeze this down here. If theta is equal to the inverse sine of 1/3, then we can draw that, try to squeeze this in here. That's going to make this 1 and this 3. And so 9 minus 1, that's 8. That's going to be 2 root 2. So that's the square root of 8 there, so 2 root 2. Okay, so now what I'm looking for here is the cosine of the inverse sine. So that, in other words, the cosine of theta here. So that's 2 root 2 over 3. And then 9/4. Now the sine of the inverse sine, those are going to cancel, so I'm just going to have a 2/3 there. And then I've got, again, the cosine of the inverse sine. So that's 2 root 2 over 3 again, multiplied by the 9/4. Oh no, sorry, I already got the 9/4 there. So this is going to be 2 root 2 over 3. Now if we simplify this as much as we can, see what's going to happen here. We're going to get 11 pi over 4 minus 11 over 2 inverse sine 1/3. 6 over 3 is going to give us 2, multiplying by that other 2 there is going to give us 4 root 2. And then here we've got 3 times 3 is 9, canceling with that 9. Those 2's and that 4 are also going to cancel, so it looks like at the end of this we've just got 1 root 2 there. Now those are like terms, so for our final answer it looks like we can get 11 pi over 4 minus 11 over 2 arc sine 1/3, and then combining those constants, minus 4 plus 1 is minus 3, so minus 3 root 2. Let's make sure that that's the same answer that we have here. Minus 3 root 2, negative 11 halves inverse sine, yep, so there we go. And then again, if you approximate this, you get the answer that we have here in the on the practice exam, about 2.5 if you were to approximate all that. Okay, so kind of a difficult problem. Really, what would make this problem a little bit nicer, I guess, would be, suppose I would have made that a 1/2 instead. Well, then at this point right here, the arc sine of 1/2, that's easier to find, right, rather than the arc sine of 1/3, because 1/2 is a number that's on the unit circle. Anyway, there we go. That's the method for this particular problem.